Dear students, Assalamu alaikum. Today I am again with you people. As you know that we are dealing with electromagnetic effects of current, and our today's topic is Ampere circuit law and its applications. It has three applications, and we will discuss one of them today, and the rest two in the next class. So, what is Ampere circuit law? What is its statement? What its status? Ampere circuit law, the relation between the current and magnetic field was first discovered by Ampere in the form of a law known as Ampere's law. It states that the line integral of a magnetic field induction B around or along a closed curve is directly proportional to the current I threading or passing through the closed path. That is, B dot dl is proportional to I. This is the line integral. So since it is a closed, this line integral has been taken along a closed curve. So we take the closed line integral. So it is directly proportional to I. This is the mathematical statement of this Ampere's circuit law, or B dot dl integral of B dot dl is equal to mu naught I. I forgot to write its subscription naught. So it is B dot dl is equal to mu naught I, where mu naught is the constant of proportionality, and this constant is known as permeability of free space. This constant is known as permeability of free space. So I have used here bold letters for vectors. I am not using arrows. So wherever you see a bold letter, so for example, B is bold, and you can see I is not bold. So I is a scalar and B is a vector. So similarly, DL is a vector. So I use bold letters for vectors here. So let us prove that this law, Ampere's circuit law, let us prove it. Let us consider a long straight conductor XY. XY is a long straight conductor carrying current I in the direction from X to Y. Suppose that the current is flowing from down to upwards, from below to upwards. So the direction of current is from X to Y. We know that, as our issue told us, that a magnetic field will be produced around this conductor. By magnetic effect of current, we know that a magnetic field will be produced around the conductor. The magnetic lines of force or concentric circles. The magnetic lines of force here would be concentric circles. Some circles will be close to the conductor, some will be away from the circle. So I have just chosen one out of those circles, magnetic lines of force or magnetic field line. I have just chosen one. There can be thousands of these magnetic field lines, and their shapes would be circular. By a right hand thumb rule, perpendicular to the plane of paper. Perpendicular to the plane of paper. Remember this thing. The magnetic lines of force are concentric circles. By right hand thumb rule, the direction of the magnetic field here is given by right hand thumb rule. As I already told you, we have to hold the conductor XY in our right hand, and if the current flows in the direction, thumb points in the direction of the conductor, then the fingers will encircle the conductor in the direction of magnetic field lines, or what we call them magnetic lines of force. So these magnetic lines of force, if we draw a tangent to them as I have drawn here, it will be perpendicular, either pointing inside the paper or pointing away from the paper, but it will be perpendicular to the paper. The magnitude of the magnetic field induction B at point P at distance r from the conductor is given by B is equal to mu naught I upon 2 pi r. We have already derived this relation for a straight conductor. When a current flows through a straight conductor, then the magnitude of the magnetic field at a distance r from the conductor, where r is perpendicular distance of the distance of the point P from the conductor. So the magnitude of the magnetic field at that point P is given by B is equal to mu naught I upon 2 pi r. The direction of B at every point is along the tangent to the circle. So since the magnetic field here it is circular in shape, if we want to find the direction of the magnetic field at that point, we have to draw a tangent at that point. Now let us consider a small element dl of this circle of radius r. As I have just chosen one circular field line, so let us take a small element of this circle of length dl at point P. The angle between dl and B is same. It is not same. It is 0. The angle between dl and B is 0. That is theta is equal to 0. Now let us make a line integral of B, that is magnetic field B, and dl, which we have considered, which we have taken small element dl. So B dot dl will be equal to B dl cos theta. We know that A dot B is equal to AB cos theta. We have learned about it in class 11th. The dot product of two vectors A dot B is equal to AB cos theta. Similarly, B dot dl is equal to B dl cos theta. As I have told you already above, or you can see from the fig, theta between B and dl it is 0. So it will be B dl cos 0. And we know cos 0 is 1. So it will be B dl. Since B is constant, it is magnitude of B is constant everywhere. So B is equal to B dot dl becomes equal ultimately becomes equal to B dl. We take this B out of the integral. Now what is dl? In here in this case, since the magnetic line of force or magnetic field line is circular, so dl is the total length of this circle, which is equal to circumference of the circle, and it is equal to 2 pi r. So B dot dl will become equal to B 2 pi r. So here we substitute the value of B from equation first. We substitute the value of B from equation first. We get B dot dl is equal to the value of B is mu naught I upon 2 pi r into 2 pi r. So 2 pi r and 2 pi r will cancel. B dot dl will be equal to mu naught I. So this is the proof of Ampere's circuital law. Now let us discuss some of its applications. Ampere's circuital law has here it has three applications. We will find uh, the magnetic field due to a straight conductor, then or infinitesimally long wire. Then we can find magnetic field due to solenoid, straight solenoid using this Ampere's circuital law. Similarly, we can find a magnetic field B due to a toroid or toroidal solenoid. The first one we will discuss in this class, and second and third one we will discuss in the next class, inshallah. So what is the Ampere's first application? We use this Ampere's law to find the magnetic field due to an infinite long straight wire or conductor. So let us consider a long straight conductor XY again. This is, you can repeat this in the same way as we have when we were proving Ampere's circuit law. This is the same case. XY carrying current I in the direction from X to Y. The magnetic field is produced around the conductor. The magnetic field lines or magnetic lines of force are concentric circles uh, as is given by us, explained to us by right hand thumb rule, RHT, right hand thumb rule. They are concentric circles perpendicular to the plane of the paper as shown in figure E. The direction of B at every point is along the tangent to the circle. As I already told you, we have to draw a tangent to the circle if we want to find the direction of field at any point on the circle. We have to draw a tangent. The tangent will give us the direction of the field at that point. So let us consider a small element dl of the circle of radius r at point P. The angle theta between dl and B is 0. That is theta is equal to 0. Now B dot dl is equal to B dl cos theta is equal to B dl cos 0 is equal to B dl. Where again dl is the total length of this circular field line, that is the circumference of the circular field line or circle here in case. So it is 2 pi r. Or BDL is equal to B 2 pi r. Let us denote this equation. Let us denote this equation by equation 1. Now applying Ampere's circuit law, Ampere's law, which tells us that BDL is equal to mu naught I. So from these two equations we see that LHS is same, so RHS will also be same. This implies B 2 pi r, the right hand side of first equation must be equal to the right hand side of second equation. So B 2 pi r is equal to mu naught I, which implies B is equal to mu naught I upon 2 pi r. This is the same expression which we have derived for the magnetic field due to a long straight conductor in the earlier part of this chapter. So but there we did not use Ampere's circuit law. Here in this case we use it Ampere's circuit law. So this was the first application of Ampere's circuit law. It enabled us to find the magnitude of the magnetic field at any point around a straight or infinitesimally long straight wire or straight conductor. So inshallah the rest of the two applications we will discuss in the next class. Thank you.